any epsilon, whatever you're saying. It's like,
all right. Welcome back to the in-person version of NETS 412, or I guess we've now added zeros to the end of all of our classes. So NETS 4120. Happy Valentine's Day. And just to sort of check off the sort of administrivia, hopefully everyone turned in their second problem set just now. The third problem set is out. It's due in 2 weeks. There's only 6 problem sets in the class, so this means we're approaching the halfway point pretty good. And are there any questions before we launch in? Okay. So let's see. So I want to, oh, yes. It's a good question. Should I release the answers? Certainly you can like ask in office hours or on Slack what the answers are, and I will tell you the answers. But I'm not sure I want to like post a document with them. Yeah. So let's see. Other questions? So I want to, if you sort of remember, in the first lecture, we sort of spent a bunch of time thinking about, all right, like we've got this general principle in game theory that play should end up at stable states of the game, whatever that means. And then we sort of thought for a little bit about various ways of formalizing that, and we sort of had a whole host of solution concepts. We sort of thought about dominant strategy, Nash equilibria, things you could find by iterated elimination of dominated strategies, pure strategy, Nash equilibria, mixed strategy, Nash equilibria. And there were problems with some of these early ones, like there aren't always dominant strategy, Nash equilibria, for example. There aren't always mixed strategy, or sorry, there aren't always pure strategy, Nash equilibria. And by the time we got to mixed strategy Nash equilibria, happily we had Nash's theorem that tells us that at least these things, at least in finite games, they always exist. So at least we've got a way to, in principle, like put some technical wood behind this otherwise nice sounding premise that like play should end up in stable states. Like we had a formal way of defining what is a stable state that like in principle led to a prediction in any game because Nash proved that every game has a mixed strategy Nash equilibria. And in some kinds of games, these predictions are even computationally plausible in the sense that if we're in a congestion game, best response dynamics will get us quickly to an approximate pure strategy Nash equilibria. If we're in one of these generalized n-player zero-sum games, multiplicative weights and more generally no regret dynamics get us to some kind of equilibria. But in this lecture, I want to think about enlarging the circle even further. Just as we sort of generalized from dominant strategy equilibria to pure strategy equilibria to mixed strategy equilibria, I want to generalize, one layer up, and why? Like, why would we want to generalize even further? Well, mixed strategy Nash equilibria exists in every game, but so far our sort of stories for why Nash equilibria are computationally plausible predictions have been sort of piecemeal. Like, we picked a couple classes of games and gave like different stories for each class of games. The hope is to, by generalizing even a little bit further, to get some class of equilibria that we can think of as computationally plausible for every game. Okay, and those are going to be correlated equilibria. Okay, so okay, I think this is probably telling that story. We've seen simple dynamics that converge to Nash equilibria in congestion games, in separable zero-sum games. And so you might at some point think to yourself, okay, like if we are sufficiently clever, then maybe we can find some class of dynamics that like doesn't care about the structure of the game. It just converges to Nash equilibria, mixed strategy Nash equilibria in any game. But for various complexity theoretic reasons, that appears to be unlikely. Although, just as we as a community of computer scientists and mathematicians, we're unable to even prove that p does not equal np. So could be that there's efficient algorithms for all sorts of things. There are reasons to think that it's in general hard to find Nash equilibria. You can define a complexity class called PPAD, which is sort of about finding general fixed points for general, n-dimensional functions. And it turns out that the problem of finding Nash equilibria is complete for this complexity class. So in some general sense, if you had a polynomial time algorithm of any sort for finding Nash equilibria in arbitrary, even 3-player games, maybe even 2-player games, you could find fixed points for arbitrary functions, and people have tried, and it seems hard. So there's reason to think that we're not going to find some even polynomial time algorithm, let alone a sort of efficient decentralized dynamic that converges to Nash equilibria without needing some additional structure in the game. But maybe there's some more general kind of equilibrium. Maybe we can sort of enlarge the circle further, just as we have up until mixed strategy Nash equilibria so far, that will take us, when we went from pure strategy Nash equilibria to mixed strategy, we got existence. Maybe when we go another level up, we can get computational tractability. And that's going to be one of the motivations for this lecture. Okay. That's sort of the motivation for the class. We're going to go into some details now, but questions about the general story and how it fits into the story we're sort of weaving in this class. Okay. So let's go back to these sort of 2x2 anecdotes from classical game theory. How many of you guys know how to drive? How many people have a driver's license? Okay, so for anyone who knows how to drive, you will be familiar with the traffic light game. Okay, so I've got a 2-year-old son who's learning about traffic lights in daycare, and he's got this song. I won't attempt to reproduce the tune, but the lyrics are something like, red means stop, green means go, yellow means move very slow. And I'm not sure about yellow, so let me remove yellow from this story. I don't think that's an accurate description of what yellow does. So let's imagine a world in which stoplights have just 2 lights, like red and green. It's clear what those mean, at least. Okay. Now, we use stoplights at intersections where, there's, let's say it's like a plus intersection. So, there's oncoming traffic potentially going in the other direction. And when you get to this intersection, you've got a game with the other person perpendicular to you at the intersection. And let's say you've got 2 actions. You can stop or you can go. Okay. And so we can sort of draw out a game matrix for what the payoff function might be. We could both stop, in which case, nothing bad happens to us, but we're also not getting to where we're going. So maybe we both get payoff 0. Or you could stop and I could go, in which case I get to where I'm going. I get payoff 1, you get payoff 0. Vice versa, I could stop and you could go. I get payoff 0, you get payoff 1. And of course, we could both go, but then we would die horrible, fiery deaths. And let's write that as payoff minus 100. Okay, so okay, if you know how to drive, you're you've encountered this game before. So yeah, I want to think about the Nash equilibria of these games, of this game, and whether the Nash equilibria are expressive enough to describe the kind of behavior that we might want to see at an intersection like this. So first of all, who can tell me what are the pure strategy Nash equilibria of this game? That's right. So if we're just looking at pure strategy equilibria, no randomness, there's two of them, right? It's a symmetric game. I can go and you can stop, or vice versa. Okay, and it's an equilibrium because if I'm going and you're stopping, there's no oncoming traffic. I don't want to switch to stop. That'll just slow me down. And you don't want to switch to go. That'll lead to a collision. Okay, and the situation can be reversed as well since everything's symmetric. So there's two pure strategy Nash equilibria. I go, you stop, I go. Okay. Now, of course, these equilibria aren't great because all of the utility here is accruing to like just one of the participants in this game. Like it's a symmetric game, but like one person's getting to go to their destination, the other person's not. The utility is 1, 0. So at least these don't seem like like maybe this equilibrium is like okay from a welfare perspective, but like it doesn't seem like a good way to coordinate society. It's not like a fair equilibrium. But things could get worse. Those aren't the only two equilibria. There's also a mixed strategy Nash equilibrium. Okay, and we can think about how we might work out what that is. So it's a symmetric game, so there's probably a symmetric equilibrium where both players stop with probability p and go with probability 1 minus p. And so, since it's just a two-action game, like that equilibrium will be defined by just a single parameter, p. What is the probability that you stop? And we can sort of just, like crank through what the equilibrium must be. Like you guys showed on the homework that, the first homework, that if we're really going to have a fully mixed equilibrium with support over both of these actions, then, well, it's got to be that at this equilibrium, both players are indifferent between their two actions. I can't randomize that equilibrium between two actions that have different payoffs for me and expect that to be a best response. Otherwise, I could just put more weight on the better action. Which means, okay, I have to be indifferent between these two actions, stop and go. And I know what my utility is for stopping. It's 0 no matter what. And so at equilibrium, my utility for going also has to be 0. So I know that my utility for going, well, what's that? If I go and you stop, which happens with probability p, I get payoff 1. And if I go and you also go, which happens with probability 1 minus p, I get payoff minus 100. And so this just gives me like an equation for p. And I can figure out what is in this equilibrium, what is the probability that I go? And it's about, I stop basically, or I go basically a little less than 1% of the time. Okay, so like there's also a mixed strategy Nash equilibrium where both players independently stop with probability 100 over 101. And they both go with probability 1 over 101. And by basically any measure except maybe fairness, because it's now symmetric, like this is even worse than the pure strategy Nash equilibrium. Right? In the pure strategy Nash equilibrium, one person was getting payoff 1, the other person was getting payoff 0. So like at least someone was getting positive payoff. The social welfare was 1. But in this mixed strategy Nash equilibrium, first of all, both players have expected payoff 0, right? Like, like now things are symmetric at least. Both players get the same expected payoff, but it's not 1, it's 0. And it's 0 because there is a, non-trivial risk of like huge negative utility, right? Like it's like what we're seeing here is basically just a failure to coordinate. Okay. So like, what's a good way to think about what is happening at this mixed strategy Nash equilibrium? The two players are each independently randomizing, right? With a probability about 1%, they're going. With probability about 99%, they're stopping. But but there's two of them. And when they both independently randomize, what that's doing is it is inducing a distribution over the 4 states of the game. Stop, 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 go, stop, and go. And it's, more or less this distribution. Roughly 1% of the time, I go and you stop. That's a good state. Roughly 1% of the time, I stop and you go. That's a good state. About 98% of the time, most of the time, neither of us go. Like, just nobody makes any progress here. And then some, like small but like non-trivial fraction of the time, we die in a head-on collision. Okay, so like, when you look at the distribution over game states, this is a very inefficient outcome, right? Like, sort of what we'd really like is almost all of the time to be in sort of the good states where one person stops and one person goes. Okay, like much better would be if we could sort of rig things up so that this was the distribution over game states, where we're never wasting time. There's always somebody going. Maybe it's symmetric, it's fair. Half the time I'm going, half the time you're going. And we never crash. Like, ideally, we'd like to be here. The pure strategy Nash equilibria sort of can get us 100% of the time on either one of the diagonals, but don't randomize in this way. And the mixed strategy Nash equilibrium is doing something terrible. It's, spending like less than 2% of the time in the good states. Okay, so one question is there maybe we just computed a bad mixed strategy Nash equilibrium? Like, is there a different mixed strategy Nash equilibrium that can induce this distribution over the game states? And if not, why not? Yeah. Yeah, it's like even worse. It's not like a failing of like the idea of stability in the Nash equilibrium. It's like mixed strategies as we've defined them aren't even expressive enough to represent this distribution over game states, right? Because the way we've talked about mixed strategies, I come up with some distribution over my actions, like 1% of the time I go, 99% of the time I stop. You come up with some distribution, and then we sample independently. Like, there's no mechanism for us to coordinate our sampling. I can't say, when I stop, you go, and when you go, I stop. Okay, so like, the only distributions over game states we can induce are like product distributions, distributions that can be like decomposed into an independent distribution over the rows and an independent distribution over the columns. Right, so if I am going half the time and stopping half the time, and you are going half the time and stopping half the time, which is what's happening here, then we would get, we would actually be in sort of all 4 game states with probability 25% each. That would be a terrible outcome. And there's just like no, there's no way, like forget incentives, there's just no way to induce a distribution over game states that looks like this without some explicit mechanism for coordination. Like, I would have to talk to you in order to arrange for something like this to happen. It just can't happen through independent randomization. There's no way to decompose this distribution over game states into an independent distribution over actions for the column and row player. Are there questions about that? Okay, so like, it's clear that we'd like to induce behavior like this. And the reason that we can't is not that this is somehow irrational, it's not that acting like this would be against someone's interests. It's not that this is violating an equilibrium condition. It is rational, right? Like, if you are out there driving. And when we're driving, we don't have to sample our actions independently. We have coordination mechanisms, which are traffic lights. It's not that the reason, one of the reasons maybe I stop at red lights is because I'm a law-abiding citizen and I, just like following rules. But that's not the only reason. Like, if it's actually like a busy time of day, it is not a good idea for me to run the red light, because I know that when I have a red light, the oncoming traffic has a green light. And there's a good chance that if I run the red light, I'm going to get hit. Right? Similarly, when I see a green light, I go not just because that's the rule, not just because I remember this song from preschool. I go because it's a good idea. Like when I have a green light, oncoming traffic has a red light. If they're playing according to this equilibrium, then I'm pretty sure they're going to stop. And so going actually is in my best interest. Right, so there's a sense in which, like, you can imagine talking about a distribution over game states like this as an equilibrium. It's sort of rational for people to play like this. Given that your opponent is sort of playing like this, you wouldn't want to deviate. The problem is the notion, like the only way we've talked about so far modeling play of a game is through independent randomization. And without coordination, there's just no way to induce this distribution over game states. Okay, and so at a high level, one of the main ideas behind correlated equilibria is to think about the kinds of behaviors you can induce rational players to play by means of a correlating device. Okay, if I have the ability to put up a traffic light that, you can think of it as giving instructions for what one player should do in a way that is correlated with the instructions given to other players. But I still can't like force people to do what I want. So I can't just give them instructions to play whatever my goal is. I still need to rely on the fact that they will think about whether it is a good idea to follow my instructions. The question is, what kind of behavior can I then induce? Okay, and so like a traffic light wouldn't work if it said, if it gave a green light to the oncoming traffic at the same time it gave a green light to me. Like then I would ignore the traffic light. The reason it works, not just on a legal level, but on an incentives level, is because it's correlating the signals, correlating the instructions it's giving to me and oncoming traffic in a way that implies it's a good idea for me and for the oncoming traffic to follow the suggested action, go or stop. Okay, questions about traffic lights? Okay, so let's try to generalize this intuition that we get from traffic lights. So let's see, maybe before we go into the parsing the definition, let's try to get some intuition. So think about a correlating device like a traffic light, except now, instead of having 2 or 3 colors, it could have 27 colors, it could have 86 colors, and more generally, like without loss of generality, the correlating device can be thought of as proposing an action for you to take. Okay, so the traffic light would work just as well if instead of green and red, it like said go and stop. In fact, like that's sort of without loss of generality, because if I have some fancy correlating device that shows colors like a traffic light, green and red, well, if people are going to think about what is their best response given the color that is shown to them, well, they'll come to some conclusion. They'll say, well, given what everyone else is like doing, given that I see green, I should go. Okay, so like the first, little twist I want to put on traffic lights is I want to imagine that the traffic light is not showing you a color, but it's just directly proposing an action that you should play, like go or stop. And we could think about this in a general game, not just a game with two actions. So the correlating device is just allowed to basically whisper in your ear an action you should play, a suggested action. Now, the reason the traffic light works is because the suggestion it's whispering in my ear is very directly related to the suggestion it's whispering into the ear of the driver in the oncoming traffic. Right? Like I know that if the traffic light whispered go in my ear, it whispered stop to the driver coming at me in the oncoming traffic, and vice versa. That's why it works. So more generally, we can think of a correlating device as corresponding to a distribution over action profiles, one for each player. Okay, so the traffic light is a distribution over two action profiles, go stop and stop go. Okay, like whenever it suggests go to me, it suggests stop to my opponent and vice versa. But more generally, a correlating device could be thought of as just a distribution over action profiles. So there's a big bag full of action profiles, one for each action. And what happens when we come up to the stoplight is someone pulls an action profile out of the bag and whispers into each of our ears the suggested action that corresponds to our coordinates in this action profile. Okay. Now, we know what distribution over action, like we, the drivers, the players in this game, we know what the distribution over action profiles is. We know the definition of the correlated equilibrium, right? Like that's important. It's important that I know that when I'm told to go, you're told to stop, and vice versa. And so more generally, given that I know this distribution over action profiles, when I hear whispered into my ear by the traffic light the action that I've been suggested to take, conditional on that being what was whispered into my ear, I know the distribution on actions that all of my opponents have been suggested to take. Like in the traffic light game, it's pretty simple. I know that if I've been told to go, you've been told to stop deterministically. But in general, it might be more complicated. Like I might not know deterministically what you've been told to do, given what I've been told to do. But I know I have distributional information about it. I would know what is the distribution on suggestions given to all of my opponents, given what I've been told to do. And so here's what a correlated equilibrium says in math, but in words, it's this. The suggestion that was whispered into your ear should be a best response, even conditional on that suggestion, right? Like conditional on the suggestion, you know a distribution on what everyone else is going to do. And among all of the actions that you could play, given the distribution you know on what everyone else is going to do, it should be a best response for you to play the action that was suggested to you. So the action that was suggested to you should be a best response to the induced distribution on what everyone else is going to do simultaneously for every player. Okay, so just writing that in math, D is a distribution over action profiles. And just to sort of unpack this compared to like when we were talking about mixed strategy Nash equilibria. Now, mixed strategy Nash equilibrium, we had not directly a distribution over action profiles, but n independent distributions over actions, one for each player. And the distribution over action profiles was just sort of induced by having every player independently sample from their own action distribution. The fact that a correlated equilibrium is directly a distribution of reaction profiles allows, as per the name, for the action profiles to be correlated with one another. Learning what I'm supposed to do in the correlated equilibrium actually gives me information about what you're going to do. And so what it says is that it should be, I might consider how I'm going to play this game. I could just say, it's a great idea to follow traffic lights. I'm going to play according to the correlated equilibrium, which just means, whenever an action is going to be drawn from this correlated equilibrium distribution, and I'm just going to play it. I'm going to play whatever is suggested to me. Okay, and if everyone else does the same, then my expected utility is, well, it's just my expected utility over a randomly drawn action profile from this correlated action profile distribution. On the other hand, I could consider deviating from it in some way. What are the kinds of deviations I could consider? Well, I see the output of the correlating device. So in principle, I could consider deviations that are a function of that, right? Like I could, if green means go and red means stop and yellow means go very slow, I could go really fast when I see yellow, but stop when I see green and go when I see red. Like I could see, I could do things that are a function of the correlating device. And this condition is saying you can't benefit by doing anything like that. And even conditional on the suggestion that's been whispered into your ear, there's no other action AI star that will gain you higher utility. Right? So not just, in the stoplight game, is it better to follow the stoplight than to just go all the time? It's also not a good idea to go when there's a red light and stop when there's a green light. Like in general, you can't improve over playing your part of the correlated equilibrium, even after you see what your part of the correlated equilibrium is, assuming everyone else is also doing the same. Okay, does that make sense? So it's very much an equilibrium definition in the same spirit we've been thinking about them. It's sort of saying, nobody can unilaterally improve by deviating from this sort of plan of action. But now there's this means by which players are coordinating with one another. Like the distribution of reaction profiles might be go stop half the time and stop go half the time. Right? And to physically implement this, you'd need a correlating device like a traffic light, but we have those. Okay, so are there questions about yeah. Not necessarily. Like it could be that, like the traffic light is, a little broken or something. And, what I know is that if I see green, 99% of the time you see red, right? So it doesn't have to be the way a real traffic light is deterministic. It doesn't have to be that I know exactly what you're going to do given what I'm told to do. Yes, so like a valid distribution could be, 99% of the time it's either red, green or green, red, but, half a percentage of the time it's, green, green, and half percent of the time it's red, red or something. In which case, if I saw green, I would now be pretty sure, but not certain that you were going to see red. Does that make sense? Other questions? Yeah.
Why is given AI not given A minus I? Like, aren't you given all the other profiles?
No, so you only see your suggested action, not the others. Okay, so like, at a traffic light, oftentimes I can see that it's red for me. Depending on the setup of the light, I might not be able to explicitly see that it's green for the others, I'm pretty confident that it is because I know the distribution on the correlating device, but I don't directly get to observe it. And so it's the same setup here.
Like if you put that from the equation, like why can't you just leave it off?
Which term?
Like, why do you have to?
Oh, we'll see a weaker version of this where in a few minutes where we do leave that off, but that's a weaker definition. Like it might be. We'll talk about this in a few minutes, but like, yeah, you could imagine something like this that just says, look, you can. I guess I can't cover things up very well on a projector, but it says, look, you can either play according to the correlated equilibrium, or if not, we will revoke access to the correlating device entirely. You will have no information, and so basically your only option will be to play fixed actions or distributions over actions. You'll no longer be correlated with what other people can do. And we could say, okay, it should be like a better idea for you to like opt into the correlation than to do anything else. This is asking for something even stronger than that. Not only is it a better idea for you to opt into the correlation than sort of going off on your own, but that even there's no sort of way you could beneficially deviate even using the correlation, right? Like you could consider deviations that use the signal you've seen, and even those are not beneficial. But we will talk about the variant you asked about. Yeah. So let's see. So this is saying for every, I guess really it should, yeah, like maybe a better way to write this would be for every possible AI and for every possible deviation AI star, it's not a good idea to deviate from AI to AI star. So even if I restrict attention just to sort of the event where you're suggested to play AI, even on that sort of restricted distribution, AI is the best response simultaneously for all actions AI. D is the distribution over recommendations. So like in the stoplight game, like the stoplight, the distribution D, the stoplight implements is the distribution over the two action profiles. Half the time it's stop go, half the time it's go stop. So the object that is or is not a correlated equilibrium is a distribution over action profiles. Yeah. Yes, so just like in a Nash equilibrium, the idea is it's a good idea for you to follow your part of it, assuming everyone else is following their part of it. Same here. Like it might be that, yeah, if other people are not following their, if everyone else is just zooming through the intersection, ignoring the traffic light, it might not be a good idea for you to go when it's green. But this is saying, if everyone else is following the recommendation, you should too. So it's sort of a stable state in the same way that a Nash equilibrium is. Yeah. That's what makes it like a stable state. Like just as in a Nash equilibrium, everyone's playing a best response given what everyone else is doing. Here, given that everyone else is following their recommendation, it is a best response for you to follow your recommendation as well. For every recommendation that you would get under this correlating device. It might be that for some recommendations, you shouldn't follow it. So maybe, maybe there's a third light that's blue, and blue means go also. But when it's blue for you, it's also blue for the other guy. And when you're told, go in the blue intonation, it's like actually not a good idea for you to go. In which case there would be in which case you might still want to follow the recommendation sometimes when it says green or red, but when it says blue, you'd want to deviate to stop. Make sense? Good questions. Other questions? Okay, so in words, it's just a distribution of reaction profiles so that the recommendation that you get as part of this action profile is actually a best response for you to play, even conditional on the action profile you've been recommended to play, the action you've been recommended to play, which tells you what distribution you expect everyone else to play according to. Okay. So one thing I want to note is that this is a generalization, just as pure strategy Nash equilibria, generalized dominant strategy Nash equilibria, and mixed strategy Nash equilibria, generalized pure strategy Nash equilibria, correlated equilibria, generalized Nash equilibria. Okay, like Nash equilibria are correlated equilibria. They're just the special case where there's no correlation, right? Like if everyone is randomizing independently of one another, that does induce some distribution over action profiles, right? Like if I play rock, paper, scissors, independently with probability 1/3, and you do the same, there's now a distribution over action profiles, we play rock, rock with some probability, we play rock, scissors with some probability, et cetera, et cetera. But it is a distribution in which the two actions are independent. And so learning my part of the recommendation tells me nothing about your part of the recommendation because there's no correlation, right? Like if we're playing rock, paper, scissors, and I close my eyes and pick a random number and decide for myself that I'm playing scissors, that does not give me any information about what you're going to play. And so in particular, something that, right, like in particular, if I was playing a best response to your distribution, which is what it means to be at a Nash equilibrium, and our distributions, the distributions on our actions are uncorrelated, I am in particular also playing a best response to your distribution, even conditional on the realization of my own action, just because if our distributions are independent, the realization of my own action doesn't change the distribution on your action, right? Like if I'm playing, if uniformly randomizing between rock, paper, and scissors is a best response to what you're doing, it is still a best response to what you're doing, even after I decide for myself, just in my head, that I'm going to play scissors this round, because that doesn't actually contain any information about what you're going to do. Okay, so Nash equilibria are also correlated equilibria. They just are correlated equilibria such that the distribution happens to be independent. But just as mixed strategy Nash equilibria were a useful generalization of pure strategy Nash equilibria, they were a larger set. There were mixed strategy Nash equilibria that were not pure strategy equilibria. Correlated equilibria are a strictly larger, richer set than mixed strategy Nash equilibria. We saw an example of that already in the traffic light game, right? We saw a correlated equilibrium that was not a Nash equilibrium. It was something different. Now, in this case, it was just a distribution over pure strategy Nash equilibria, right? Because both of these corners were pure strategy Nash equilibria. On the homework that just went out, though, you're going to sort of work out an example where it can go beyond that, right? You can have correlated equilibria that are truly different than any of the Nash equilibria in particular that can have higher social welfare than any of the Nash equilibria. Okay, so just to sort of maybe draw a picture that's good to remember, we've got dominant strategy equilibria here. We've got pure strategy Nash equilibria, that's a strictly larger set. We've got mixed strategy Nash equilibria, it's a strictly larger set. And we've defined this set here, correlated equilibria. It's said here, correlated equilibria, that again generalizes mixed strategy Nash equilibria, but contains other stuff, contains mixed strategy Nash equilibria, but also other stuff. It's a larger set. Okay. Why don't we continue? we can define even larger sets. And so there was a question about, what if we don't condition on the suggestion that's been whispered into our ear? What if we just say something like this, like giving someone two choices. Either you can opt into the correlation, you can experience utility equal to the expected utility of the action profile sampled from this correlating device, or you can opt out of the correlation and do something else, but I will no longer show the correlating device to you if you do that. So you no longer have the option to consider deviations that are a function of the signal that you get. Your deviations have to be just fixed actions or mixed strategies that don't depend on the correlating device anymore. So the alternative is to obtain utility sort of from the action profile that arises when you play some fixed action and everyone else continues to use the correlating device. And the rationality condition here is that for everybody, it should be better to opt into the correlating device than to opt out. Like your utility for opting in and getting payoff according to this sort of correlated action profile should be only larger than the utility that you can get by setting out and doing your own thing. Okay, that's called a coarse correlated equilibrium. The only difference between this, a coarse correlated equilibrium and a correlated equilibrium is whether the set of deviations you are allowed to consider are allowed to depend on the correlating device. In a correlated equilibrium, you can consider deviations after you've seen the suggestion that you would have gotten in the correlating device. In a coarse correlated equilibrium, you have to consider deviations before you've seen the suggestion. Okay, so you can imagine by way of only slightly strained example that now when we have cars that are driven manually or maybe beginning to have self-driving cars, but the technology is still new enough that the cars have to do what we say, that if you imagine a service like Waze or Google Maps that's going to give us a suggestion, like it's going to suggest a route for us to drive along, but it can't force us to do it, right? Like after we see the suggestion, we can decide if we want to do it or not. That such a service could try to implement a correlated equilibrium, right? It could sort of try to correlate the suggestions it gives to different drivers so that to get some good outcome, like to minimize congestion time or something. But if it wanted people to follow the suggestions, like the suggestions would have to be good ideas even after I saw the suggestion. Like if you thought that you could get benefits in social welfare by occasionally telling me to drive some really out of the way route in order to free up, road capacity for other people, like on those days, I would just not do it. Okay, because I could deviate after seeing the suggestion. On the other hand, you can imagine some, world in the future where maybe I have the option to buy a fancy self-driving car that's plugged into the, national optimization network, or I have the option to, use my old legacy car that's not, but that the self-driving car, it's not going to have a steering wheel. Like it's really going to drive itself. I'll tell it where to go, but it'll decide on the route. Okay. In which case, like my choice point here is at the moment when I'm deciding what car to buy. I can opt out of the correlation. Right? I can opt out of the correlating device by buying like an antique car that has a steering wheel. Or I can opt into the correlation by buying one of these modern networked cars. But if I do that, I'm not gonna I'm gonna lose fine-grained control on about which route I take on which particular day. And then maybe if you wanted to incentivize people to opt into the network cars, it would be enough to implement a coarse correlated equilibrium. Coarse correlated equilibrium says, on average, you're going to be better off sort of opting into the correlation. You'll be better off on average than, doing anything that doesn't get access to these correlating signals, anything you could do with your sort of antique car. But there might be particular days when, if only you knew the route it was going to take you to, tell you to take that day, you would have preferred to deviate. You just didn't have the option. Okay, so maybe that's some high level intuition about the difference between these two solution concepts. Yeah, so whether a coarse correlated equilibrium is a sensible solution concept depends on whether in the interaction you're thinking about, the players have the option of deviating after they see their suggestion, or whether the only point at which they could deviate is before they see their suggestion. A coarse correlated equilibrium says it's a good idea to opt in before you see your suggestion in expectation over what the suggestion is going to be. A correlated equilibrium says it remains a good idea even after you see the suggestion. Okay, so another difference between correlated equilibria and coarse correlated equilibria. Coarse correlated equilibria can occasionally suggest things that are just on their face a bad idea, so long as it doesn't do it too frequently and the benefits that you get from correlation elsewhere are enough to sort of counterweigh these occasional, obviously bad suggestions. Whereas correlated equilibria can't do that. Correlated equilibria can only make suggestions that are good suggestions given what you know. Okay, so just to sort of give an example, suppose I've got a game that looks like this. Maybe, it's sort of a simple coordination game in the upper quadrant here. We'd either like to both play A or both play B, but if we miscoordinate, that's no good. And then maybe there's this obviously bad move C that, if we both coordinate on C, we get even worse payoff than anywhere else in the game. Okay, so we can think about the following distribution on action profiles: that a third of the time suggests that we both play a third of the time suggests we both play B, and a third of the time suggests we both play C. So this is not a correlated equilibrium, because if I get the A suggestion, great, I'm going to play A. It's a great idea. If I get the B suggestion, great, I'm going to play B. It's a great idea. But if I get the C suggestion, well, I know that if you play according to the correlated equilibrium, you're going to play C as well. I would be better off playing A or B. So it's not a correlated equilibrium because one of the signals, C, is not a best response conditional on that signal. On the other hand, it is a coarse correlated equilibrium because suppose I opt into the randomness. I'm getting gains from the coordination here. 2/3 of the time, the coordination is actually helping me. It's only a third of the time that the coordination is hurting me. So if I opt in, 2/3 of the time I benefit from the coordination. A third of the time I get payoff 1. Another third of the time I get payoff 1. The last third of the time, I kind of got screwed over. I get payoff minus 1.1, but still, on average, my payoff's pretty good. It's 0.3. If I compare that to how well I could do by opting out of the coordination, well, how well could I do? Well, if I no longer have access to the coordination signal, it's not like I can say, okay, I'm going to follow the suggestion if it's A or B, but I won't if it's C, because I no longer see the suggestion. So really, the only thing I can do is play a fixed action or a fixed distribution over actions. So what happens if I play a fixed action? I could play A while you randomize like this. But in that case, like, a third of the time I'd get payoff 1, a third of the time I'd get payoff -1, and a third of the time I'd get payoff 0. And so my payoff for playing A would just be 0. Similarly, my payoff for playing B would just be 0. And for playing C would be negative. So opting, like, despite the fact that this coordination mechanism a third of the time tells me to play something dumb, like, I'm still on average gaining more from the coordination than I'm losing. I'm better off on average following this coordinated strategy than doing anything that's independent of the coordination. So it is a coarse correlated equilibrium. Does that make sense? This is maybe like the salient difference between a correlated equilibria and a coarse correlated equilibria. Like, a coarse correlated equilibria can be a good idea to play just by virtue of like averages. Like, if usually you're gaining from the correlation, it can occasionally suggest something that you wouldn't want to do if only you had the option to deviate given the suggestion. But like, it's not worth opting out of the correlation entirely, because on balance, you're gaining more than you're losing through the coordination. A correlated equilibria can only suggest things that are best responses given the information available to you. Okay, questions about the difference between a correlated equilibria and a coarse correlated equilibria? Okay, so just sort of maybe adding a circle to our degenerate Venn diagram here. Coarse correlated equilibria, generalized correlated equilibria. Correlated equilibria are coarse correlated equilibria, but there are some coarse correlated equilibria that are not correlated equilibria. So again, it's a larger class. Okay. And just sort of, like, looking at this chart, what did we get? Well, at this point, when we got to mixed strategy Nash equilibria, we got existence. The goal is to show that at this next jump, we get computational tractability. So sort of by the end of next class, I want to be able to describe like an efficient learning dynamic that will converge to correlated equilibria in any game. Okay. And the way we're going to eventually get there, like the learning dynamics, it's going to be a little bit more complicated than polynomial weights, but it's going to be related. So we're going to be talking again about sort of regret, the way we talked about regret last class. It's going to be useful for us to give like an alternative definition of correlated equilibria and coarse correlated equilibria that are defining the same object, but in terms of regret, because our path to like efficient learning dynamics in games are going to be through designing learning algorithms that can guarantee the various kinds of, that players don't experience various kinds of regret. So let me define maybe a larger class of kinds of regret than we've talked about before. So let's say that a strategy modification rule, FI, is just a mapping from actions to actions. It's saying like, look, every time you played action 5, you should feel bad about it. Like you should have played action 4 every time you played action 5. And every time you played action 3, you actually should have played action 7. Okay, so it's like, think of a strategy modification rule as like a backseat driver who's telling you what you should have done instead of what you actually did. Right? Like for every action you could have played, the strategy modification rule is telling you what you should have done that maybe would have been better than that. Okay, but more generally, it's just a mapping from actions to actions. But your regret, given an action profile and a strategy modification rule, is the difference between how well you would have done if you had let the backseat driver go back and change history, change the action you actually played, into the action the backseat driver said you should have played, right? The action that you get by applying the strategy modification rule to the action you actually played, the difference between the utility you would have gotten under this counterfactual world in which the backseat driver applied the strategy modification rule compared to the utility that you actually got, given what you actually did. Okay? So a strategy modification rule tells you for everything you could have done, what you should have done instead, and your regret to a strategy modification rule given a particular action profile is just how much better you could have done had you applied the strategy modification rule. Okay, and some backseat drivers give only like simple suggestions. Like their suggestions aren't conditional. They're just like, you just should have played action 7. Action 7's the best action. Just play action 7. So if the strategy modification rule has that form, it says just play action 7. In particular, if it maps to action 7, no matter what input you give it, or for any value of 7, it's a constant function, then we'll call it a constant strategy modification rule. Okay, and so let's give an alternative but equivalent definition of a coarse correlated equilibrium, and then an equivalent but alternative but equivalent definition of a correlated equilibrium. So a distribution over action profiles is a coarse correlated equilibrium if simultaneously for every player I and for every constant strategy modification rule, their expected regret to that constant strategy modification rule is non-positive. They don't have any expected regret. Now, a constant strategy modification rule is just sort of like a obfuscated way of saying you don't have any regret to the best fixed action. Right? It's just saying like, look, in expectation, like you're better off following the correlating device than always playing action 1. And also you're better off following the correlating device than always playing action 2. Right? So it's the same definition from before. Like you're better off following the correlating device than doing any fixed thing that is independent of the correlating device. The fact that it's a fixed thing is encoded in the fact that here we're just thinking about constant strategy modification rules. Okay, so if you have no regret to the best fixed action, this is exactly the same kind of regret that the polynomial weights algorithm guarantees is diminishing, guarantees goes to 0. Right? If you play a game with the polynomial weights algorithm, you're promised that your average expected, your sort of average payoff over time is at least as high as had you counterfactually been able to go back and modify your play every day to play every day consistently the same fixed action. It's just saying you have no regret to constant strategy modification rules. So an immediate consequence of this is that in any game, if we've played the game for T rounds and have generated a sequence of T action profiles, A1 through AT, and it turns out that this sequence has low regret, let's say delta of T regret, in the sense that we talked about last class, then if I look at the distribution that results just from sort of the empirical distribution over these action profiles, the distribution that results just from picking uniformly at random one of these T action profiles, this distribution is a delta of T approximate coarse correlated equilibrium, meaning the expected regret is, okay, it's not less than 0, but it's less than delta of T. Okay. And so in particular, that means that we already know a learning dynamic that converges to coarse correlated equilibria in every game. The polynomial weights algorithm does it. Because we know that if every player plays according to the polynomial weights algorithm, then no matter what their opponents do, their regret to the best fixed action in hindsight, equivalently their regret to the best constant strategy modification rule, goes to 0 at a rate of root log k over t. And if everyone does it, everyone's regret goes to 0 at that rate. And we get a sequence of action profiles that has regret going to 0 at this rate. Regret to the best constant strategy modification rule, which we now realize defines coarse correlated equilibria. Okay, so we have a very fast dynamic converging to coarse correlated equilibria in arbitrary games. In particular, it has no dependence at all on the number of players. And it only has a logarithmic dependence on the number of actions. Right, so like this is saying in an n action game, sorry, a k action game with n players, after a number of rounds that is independent of the number of players. N can be as large as you want, and only logarithmic in the number of actions, and going to 0 at a rate of 1 over the square root of the number of rounds you've played, you're converging to these approximate coarse correlated equilibria. So this is incredibly fast convergence, depending only logarithmically on the actions and unbelievably, like entirely independently of the number of players. And so the question I want to ask, and I want to set up the question this class and then answer it next class, is can we similarly try to think of a learning dynamic that we can argue converges to correlated equilibria, not just coarse correlated equilibria. And so, like for coarse correlated equilibria, like it sort of, we gave an equivalent definition of it in terms of regret to these like constant strategy modification rules. And then we just kind of like remembered like, oh yeah, like we've been studying this polynomial weights algorithm in class. It already guarantees that that form of regret goes to 0. The strategy here will be to give a characterization of correlated equilibria in terms of a richer regret notion, one that's stronger than is guaranteed by the polynomial weights algorithm. But maybe next class we'll be able to give an algorithm that promises diminishing regret of that stronger form. Okay. So here's the sort of regret definition, the regret definition of correlated equilibrium. And it just removes the caveat constant from constant strategy modification rule. Okay, so a distribution over action profiles is a correlated equilibrium if for all players I, and now for all strategy modification rules, all possible backseat drivers who are telling you what you should have done now as a function of what you did. They might have different suggestions for different things you've done. If for all strategy modification rules, your expected regret to that strategy modification rule is non-positive. Okay, the claim is this is the same definition. This is a correlated equilibrium. Okay, so so a strategy modification rule, right? Like, what is it doing? Well, it's saying, oh, well, like every time you played action 7, you should have played action 4. Every time you played action 9, you should have played action 12. So what it's saying, that like if there are no beneficial deviations of this sort, right? Like if actually the best, like if you've totally stumped the backseat driver and says, okay, like, yeah, every time you played action 12, I guess I would have played action 12 too. Every time you played action 3, yeah, okay, fine, I would have played action 3 too. Well, like the only way that can be true for like every backseat driver is if, in fact, the action you played, which in a correlated equilibrium was equal to the suggested action you were given, if in fact that really was a best response given the suggestion, right? Like if we're playing a correlated, if D is a correlated equilibrium, right? What that means is that even conditional on seeing your suggestion, even conditional on the action you're supposed to play, that action is a best response. And so in particular, like there's no strategy, you know, if the strategy modification rule says every time you played action 5, you should have played action 3, like that's not helping, that's making things worse, because the correlated equilibrium condition was that conditional on being told to play action 5 really was a best response. Playing action 3 can't gain you anything. And if that's simultaneously true for every action, as it must be if you have no regret to any strategy modification rule, then you're at a correlated equilibrium. Okay, so this is the same definition of correlated equilibria that we saw before, just now in terms of strategy modification rules. There should be no mapping from the suggestion that you are given to the action that you should play that does better than the identity mapping. Like you should just play the suggestion. That's what it means that the suggestion is a best response to the distribution induced by the suggestion. Okay, does that make sense? So, okay, so a coarse correlated equilibria corresponds to no expected regret to constant functions, to sort of functions that can sort of go off on their own, but can't interact with the randomness of the correlating device. Correlated equilibria corresponds to no expected regret to arbitrary mappings between suggestions of the correlating device and actions that you take. You should just follow the actions. And then in asking the question, are there learning algorithms that efficiently converge to correlated equilibria, just as the polynomial weights algorithm efficiently converges to coarse correlated equilibria? We can again sort of abstract away the game theory part of it and try to approach this as a pure machine learning problem and sort of say, okay, well, the polynomial weights algorithm is a way to play in a sequential interaction that guarantees us no regret to the best action in hindsight. Can we derive a learning algorithm that goes beyond that and guarantees no regret, not just to the best fixed action, but to sort of arbitrary counterfactual worlds that would have arisen by applying arbitrary strategy modification rules? Okay, so that's sort of the approach we're going to take next class, just to like set it up here. We're going to go back to the expert learning setting, and we're going to try to derive algorithms that have stronger guarantees than the polynomial weights algorithm, but in the same setting. So we want to learn an algorithm in the same expert learning setting that can guarantee the following. Okay, so just to recall the setting, we've got these K experts, the K like actions in the game. Every day we need to pick one of them. Every day we pick an expert. And then after we pick the expert, all of the experts experience some loss, say a number between 0 and 1. We, the algorithm, experience the loss of the expert we picked. Okay. And our goal is the goal for the polynomial weights algorithm was to come up with a way of picking experts so that our accumulated loss as an algorithm was no worse, up to some diminishing regret term, than the accumulated loss of the best fixed expert. Here we have the stronger goal. We'd like to come up with an algorithm that for arbitrary sequences of losses can pick experts such that the accumulated loss of the algorithm, the sum over all of the rounds of the loss of the expert we chose at that round of the algorithm, is no more than sort of the loss we would have accumulated in the counterfactual world, where at every day t, rather than playing action AT, we played action FAT for some strategy modification rule F, where F can map arbitrary actions to arbitrary actions. Okay, so just note that asking that this hold for arbitrary strategy modification rules is strictly stronger than the guarantee that the polynomial weights algorithm promises, because doing no better than the best fixed expert just corresponds to having no regret to constant strategy modification rules. Strategy modification rules that sort of always suggest you play expert 2. Okay, so the polynomial weights algorithm promises this for strategy modification rules that are constants. It says you do as well as always playing expert 1, or always playing expert 2, or always playing expert 3. That's why we converge to coarse correlated equilibria if we play according to polynomial weights. Our goal for next class is to give algorithms that promise simultaneously for all possible strategy modification rules that we don't have any counterfactual regret to playing those strategy modification rules. Like that we are immune to like backseat drivers who can now suggest swapping actions as a playing things as a function of what we've done, causing us to regret our choices. We do at least as well as any plan that the backseat driver can come up with by using a strategy modification rule. Okay, if we can do that, then we will have a learning algorithm that if players use it to play a game, converges to a correlated equilibrium. That's going to be the plan for next class. Okay, so I'll see you guys on Thursday.